Hello, everyone. I'm really glad that you came to hear and talk about the new parser coming for Node. A bit about who I am. I'm Fedor Indutny. Here's my Twitter and GitHub handles, which are quite the same. And I write code at PayPal. You might know me by this dark side avatar from DC Comics that I use on both Twitter and GitHub and practically everywhere else. So as for today's talk, the slides of the presentations are already available online. So if you would like, you can scan the QR code and open it in your browser and just follow along as I'm going to present the topic, which is llhttp, the new HTTP version 1 protocol parser for Node.js. This topic, of course, has deep roots into the history of Node.js, and it would be hard, if not impossible, to not mention the history while describing it. Of course, Node.js recently is used a lot for front-end tooling, but originally, historically, it started as a backend platform. It was exclusively about building asynchronous HTTP servers. It is then unsurprising that, quoting Ryan Dahl, the creator of Node, that HTTP parser is what started the Node. There have been a lot of presentations on importance and the role and internal structure of libv. It powers Node.js event loop and is a key core component that makes everything spin outside of the Node. And you might be wondering if libv is the oldest dependency. However, it is not. As a HTTP parser is the oldest dependency that Node ever had. So it has actually outlived all other dependencies in Node. Initially, it was inspired by Mongrel, which is a Ruby web server with its own parser created by Zshow. Later, there was some parts of nginx code introduced in HTTP parser, the original one. And of course, a lot of original code by Ryan himself. The parser has been with us since 2009, so it's been a whopping 10 years. And in fact, the Node itself has been introduced at this very conference 10 years ago by Ryan. So it's kind of a jubilee for both of those projects. And to celebrate this, I wrote another HTTP parser to replace the original parser. So why would anyone want to get rid of such library? Of course, it's a fantastic library. It has been with us for 10 years, so it should have been worked fine. It has many users outside of Node.js community as well. For example, Envoy proxy by Google. They use it for parsing HTTP requests, and it's a quite popular project as well. So what makes this parser so great, and how did it stay with us for so long? First of all, it has good enough performance. What this means is that it takes quite a lot of time to invoke a C function from JavaScript, and parser is written in C. And it takes way, way less time to parse the request. I'm going to elaborate on it a bit later in this presentation, but for the Node.js purposes, it's a very good performance, so it couldn't be better. It also supports a lot of clients and servers that violate the HTTP specification. And there are way, way too many of them out in the internet. You would be surprised how many. And of course, supporting them was very important for early adoption of Node.js, because in 2009, there was even more such clients and servers out there. Another point is that original parser has a lot of test suites. So over 10 years, Ryan, Ben, and other maintainers of the project, including myself, we wrote quite a comprehensive test suite that covers almost every aspect of HTTP specification. So the parser is well tested. So that was a good point of original parser. Now we come to other points. Unfortunately, with the age of the library, the code became quite rigid. It became impossible to move things around, to make significant changes to it. And as a consequence of this, it became impossible to maintain this library efficiently. Furthermore, as one of the maintainers of the project, I have to constantly relearn and get familiar with the parts of the code base that I was previously familiar before. And I did it on every pull request, and still I wasn't sure if the code is going to run in the way I expected to run. So it could introduce some unexpected behavior, even though I checked it, or maybe a security vulnerability as well, which is obviously bad. It doesn't help either that most Node.js users and developers are familiar with JavaScript and are more compatible with it than they are with C. So there is not too many people interested in working on this HTTP parser. With all of this in mind, several years ago, I have set on a quest to make the library better and maybe a bit faster in the process. First attempts were quite conservative, so I tried to state with existing code as much as possible, and some of them were successful, like replacing the parts of state machine with the macros and using them consistently. This not only improved the code, but also made it faster, which was nice. Other attempts were a complete disaster. I tried to move those states into a separate function and just call them from the loop, so each state would return the next state that is supposed to be executed, and then the loop would run that function for it. This completely ruined the performance, and I never contributed it or sent it to upstream. From these attempts, both successive or failure, the conclusion was clear. It was hard to make an improvement while staying with existing code base. And if there was no requirement to reuse as much code as possible, then it was no longer necessary to develop the library in the same programming language as before. So why not develop it in JavaScript or maybe TypeScript instead? And of course, JavaScript performance is quite great, but you wouldn't be surprised that it's slower than C. And it takes a lot of effort to reach comparable performance as the C libraries when you write programs in JavaScript. It takes a lot of effort, but it's possible. So I wanted to get this performance optimization out of consideration, and thus I decided to just define the parser in TypeScript and still compile it down to a C library. So the end result would still be C libraries that could be used in Node and other projects. And which is great because existing users of HTTP parser this way would be able to transition their code to the new parser, and hopefully in the process the performance would not degrade too much, because in the end it's running on the same programming language. So it has good chances of being the same speed. So llhttp is in a way the next major version of HTTP parser. It has the same core principles and a similar API, which is almost identical. And the way they both work is that they scan the request one character at a time. And during this process, they change the internal state. And they also could embed the header fields or maybe header values. And later on, body. I'm not sure if we're going to wait for this. It's quite slow. OK, yeah, I think you probably understand what it means now, at least to some extent. So through this scanning, and by the virtue of this one-by-one scanning, the parser can work without buffering anything at all. So it doesn't allocate memory itself. And it's great, especially for the request bodies, because it could just meet the slices of original buffers that came from network instead of allocating and copying data. So it's in core principles of the HTTP parser, it is that it's not copying. That's important. As soon as any amount of data basically arrives from network, be it a half request or even a single byte of the request, the HTTP parser is ready to process it. And it will emit possibly partial, because it could be half request, the header names and values, and maybe HTTP bodies we just seen in this animation. In the original version of the parser, this scanning was quite naturally implemented over in the for loop over the input. So it was just going through the input byte by byte and doing some things. And what it did is actually it was described by huge switch statement over all possible parsing states. So whether it's a header name, header value, maybe it's a value of content length header, it was all described by this switch statement. And different clauses of this switch statement were representing different states of the parsing, of the state machine. All of this lived in a single function over 1,000 of lines of code, which is quite a terrible idea. The obvious improvement would be to break this switch into pieces and make it such that each piece has precise action in sort of a Unix philosophy, I guess. So it would be just exactly about doing one small thing at a time. Go-to statements would be used to just jump between states, so there would not be much need in using this for loop, at least not as much. So with all of this in mind, how exactly did I approach this process? I have developed a domain-specific language, or DSL for short, and developed it in TypeScript, and created a compiler around it, which is called llparse, so it's again double L. And this compiler is used to describe the parsing states in terms of these actions that they perform. So each state would have several actions assigned to them, and they would perform them and move on to the next state when it's ready. Because this llparse is quite general compiler, it can be used for other protocols as well. And it works better for textual protocols, but still, I think it could be useful. Original parsers suffered from surplus of handwritten code. So I have selected a few actions that were repeated most in the original library and made DSL around them. The idea here is that I wanted the description of the new parser in this DSL to be concise. So I wanted to write the code with the less lines and less symbols as possible. So I wanted to move the most common operations inside of the compiler so that the rest would not have to do this work all over again and repeat it as it was in the original parser. Here are a few methods that this compiler supports. One of them is match. It takes a sequence or a character of bytes, and it tries to match them from the input. For example, it could be keep alive, which is a value of the header named connection. It's a quite common header and very important. So it could match this sequence, and when it does, move to the next state by taking the reference to this state. At other times, the parser needs to check the next character in the incoming data without actually consuming it, and peek could be used for this. So it takes a single character, just matches it in the input and moves on without making any other work, so without moving forward in the input stream. And speaking of headers, headers like content lengths, they have integer values, which are frankly described by strings because it's a textual protocol. So the new parser has to be able to parse the integer strings. And the way to do it, the way I decided to do it, is to implement this select method in DSL, which takes a map as an input. And this map has sequences or characters as keys, and the integers as values. So it tries to map these sequences to the integers and just pass these values along to the next state. And the next state could be storing those integers inside of some property of the C structure, or it could be maybe invoking a user callback with them. Speaking of callbacks, there is one special type of callbacks that is very important in the lifespan of both original and the new HTTP parser. So during their execution, they emit ranges of data. For example, header names or header values are both emitted in this way. And given that we have a stream of data that comes to the parser, we have to be able to mark some certain place inside of the stream as the beginning of this range, and then at some other point later on, we want to set it as the ending of the range. So between those beginning and ending, or if you see these are beginning and ending, between them, the callback is going to be invoked for every byte. And it's really, really useful for header names, header values, for bodies, and other things that could be emitted as spans or ranges of input. Of course, there are a couple of important actions that I have omitted in previous slides and that are actually mandatory to have in the states. They called otherwise and skip to, and those specify which state of the parser should be reached next if nothing else matches inside of the current state. So in this example, if the input would be A, the parser would move to the child A state. For the B, it would move to child B, and if it would be C or D or E or whatever the letter, it would move to some other state. Skip2 is quite similar. It does exactly the same thing, but it consumes a character from the input stream. So otherwise, it does not change input stream at all. It just moves on. So that was a bit of description, maybe too concise to be useful, of the DSL. And with this DSL in mind, llhttp becomes a TypeScript program. And this TypeScript program uses DSL to define the parsing states and describe their actions and input, as I said before. And because it's a TypeScript program or a JavaScript program, really, I could split it in several submodules and use them efficiently. And each submodule could represent a subparser. And in fact, this is what I use in llhttp. I have a separate URL parser inside of it, and I can test it separately, I can run it separately, and it actually could be used separately as well, just as a separate library if anyone wants it. So llparse, a lot of double L's. llparse transpiles this TypeScript program down to C, and that's the main action of it. Note that because it uses a stable DSL, it just uses DSL, the compiler doesn't need to do any parser or syntax checking. It is done automatically by the JS engine, so V8 does it for us. So V8 just executes this DSL, and internally, llparse builds a graph of states, which I will try to show you. Yeah, it looks kind of terrible, but I probably can zoom in. Yeah. So so here how it looks like in practice. I can probably actually show you something more useful. So here on the right, you see ACL, bind, checkout. It's probably too small, but it's method names that are supported by parser. And if the method name is matched inside of the input, it will store the integer encoding of the method inside of the property of internal property of the parser. It works this way more or less. And I get to admit this kind of graph is looking awesome. So that's one reason to have it. Another reason to have it is that llparse can do static analysis on this graph. Before, in the original parser, there was no way to reason about the states automatically. So it was all described manually inside of the parser. There was just a lot of C code, and there was no way to analyze it and to do any optimizations or checks. What I can do in llparse is check the graph for absence of infinite loops, which is possible due to otherwise and peak, so they could be combined together to just not make any progress over the input and just spin indefinitely. And of course, it's very important to check this statically because there might be some rare conditions that could trigger it online, and so might be not immediately verifiable with the test suite. Speaking of optimizations, the parser could do peephole optimizations. It's a fancy name for just combining similar states together into one. This way, the amount of generated code is reduced, and also programmer has a lot more freedom in developing the parser because they don't have to think about doing these optimizations manually in their code. So as I said, the DSL is quite stable for llparse. So same program could be compiled to different outputs. At this moment, C and LLVM bitcode are both supported. And LLVM bitcode was kind of before, it was supported before the C. So that's the reason why both projects have double L in their names, kind of historical reason. But in the end, when I ran benchmarks, it turned out that this trivial C compiler worked faster than LLVM bitcode, which I spent several weeks on. Yeah, it was quite surprising for me and maybe shocking, so it took a few months to think about it. Yeah, and speaking of performance, you might be wondering how fast this new parser is, given that it's not handwritten at all. But of course, despite the maintenance issues, as I said before, the original HTTP parser has very good performance, good enough, but still very good. It would have been very unreasonable to replace it with something that performed significantly worse. So llhttp is not handwritten, it's not hand-optimized. And when I ran benchmarks, I discovered that it runs twice as fast as the original parser. Thank you. And here is actual benchmark numbers. So as you can see, both those numbers are quite wild. It represents the number of requests per second that each parser can take. And this way, both parsers run in less than microseconds. So you wouldn't ever see this on the profile logs. It's just impossible to see it. Of course, it's quite evident as well that llhttp is more than 2 times faster than the original parser, but Node hardly cares about it. This llhttp parser is the default HTTP parser in Node version 12. So if you are using the latest Node, I hope you do, you are already running this. And even more, you have a reason to blame me for any kind of HTTP problems that you have. So feel free to do so, and it will be rightful to do so. So please open the GitHub issues, though. So don't just brag on Twitter about how bad I am, and tag me on GitHub. I'll be happy to look into it and fix it as soon as possible. As I said before, over 10 years, original HTTP parser has accumulated a comprehensive test suite. It would be really unwise to get rid of it and just start it over, so I ported all original tests to Markdown and added a few new ones. And you heard it right, they're described by the Markdown files, so they're completely textual, and I encourage you to take a look at them if you want, because I find them the most amusing part of the project that I worked on. Yes, they're really, really fun. So I'm going to give a bit more time because I see that some people scan the codes. OK, so that makes it. And each Markdown file contains several tests. They are separated by the headings, so it's quite easy to read and even easier to contribute. In fact, I had one contributor that submitted the test without even asking me a question on how to do so, even though I don't know that many projects that use this test system. So it is easy to contribute. And furthermore, each test has a textual description side of them. So they have a code chunks inside of Markdown. Code chunk for input, code chunk for expected output. And between those, you can put just any text you want. You could put hyperlinks. You could put images. You can put GIFs of cats doing stuff. So it's quite nice way of writing tests. And it especially works well for HTTP because it's a textual protocol. So you can read the requests there and see what is actually fed inside the test suite. Yeah, so here's been the present of the parser and the history of it. So naturally, I would like to talk about what's coming next. And there is a room for future improvements with regards to doing more static checks on this graph that I showed to you and doing more performance optimizations. There are forks of original HTTP parsers that use CPU-specific vector instructions, which are really, really, really fast. And they perform much better than both llhttp and original parser. There's not much use for this speed bump for Node, but nevertheless, there's no reason to not explore it. So I probably should do it, or I would love to see someone doing it for me. That would be awesome. Quite shamingly, the project is not so well documented at the moment. It has considerable amount of JS doc describing the API of llpars in detail, but it's kind of scattered through several dependencies and could be made much more accessible. I would really appreciate help with this, and I'm sure that some people might find this quite entertaining as well, because there's a lot of interesting moments in the parser and its code. Finally, it would be fascinating to see different types of parsers implemented on top of llpars DSL. There's two examples that I have in mind. The SMTP and POP3 protocols, they both are textual and could be implemented quite efficiently async in llpars. So I really look forward to either working on this or helping someone with this. And yeah, here is a link to the llhttp repository. It's actually quite easy to find on GitHub. It just lives under a Node.js organization. So it's github.com/Node.js//llhttp. So I guess that's it. So thank you so much for listening.